Classical physics and standard Zermelo-Fraenkel set theory have historically struggled to map the exact boundary where continuous fractional fields intersect with discrete topologies. Pushing mathematical operations across this boundary inherently generates complex, intractable noise. Standard analytical models treat this noise as a paradox or an approximation error, a glitch that requires manual renormalization to force the equations to balance. The theory of infinity, or TOI framework, proposes a rigorous counterthesis regarding the architecture of the mathematical cosmos. It treats mathematical infinity not as an uncomputable void, but as an ontological primitive. The primary postulate of this framework treats mathematical variance at these boundaries as measurable thermodynamic heat, a physical byproduct masking an immovable, discrete geometric bedrock. To test this postulate, we anchor our investigation to a specific discrete structure, the 7th, 8th, and 9th rungs of the Fibonacci sequence, yielding the discrete algebraic shell of 13x squared plus 21x minus 34. This sequence is the core of an operation codified in the ledger as book CXV, the Fourier-Fibonacci Synthesis. The explicit objective here is to deliberately force these discrete Fibonacci masses into highly constrained, continuous fractional bounds. An operation of this magnitude requires strict auditing to separate physical geometric necessities from hallucinated computational errors. This auditing is governed by the friction versus fiction protocol, a rigid categorization system that assigns specific ontological grades to emergent mathematical anomalies. Observing whether discrete integer geometries survive a forced continuous projection under this protocol tests whether macroscopic thermodynamic systems follow the same singular geometric laws that define the integers themselves. Before stressing these integer structures, we have to establish how the framework extracts a stable, bounded cosmos from an infinite background plenum in the first place. The TOI framework operates on the principle of order ex totalitate. Mathematical structures do not emerge from an empty set. They are carved out of a turbulent, unbounded phase space of absolute totality. Filtering infinite potential requires a generative triad, the material substrate, psi, the organizing symmetry, phi, and the evolutionary focus, theta. This process is initiated by a primordial twist, an axial asymmetry introducing opposing trajectories of collapse toward a central axis. To prevent this twist from descending into an unstable, infinite recursion, the system utilizes golden arches, specifically pi and gamma. These topological constructs bridge the origin, neutralizing the primordial twist to achieve a parity-even closure. This topological closure yields the golden set. It functions as the ontological seal, creating the stable, lawful context where mathematical invariants achieve absolute self-reference. This algebraic resolution directly mirrors Galois symmetry groups, which are structures that measure the exact solvability of polynomial equations. Under this model, achieving mathematical solvability is entirely synonymous with cosmogenesis. The golden set provides a sealed environment. To test the true structural limits of that seal, we must subject a closed integer structure to the most severe continuous mathematical stress available. We return to our core discrete Fibonacci quadratic. In classical analysis, extracting the roots of this equation is a static procedure executed via the standard quadratic formula, keeping the math strictly within algebraic space. The Fourier-Fibonacci synthesis abandons that method. It forcefully rips the quadratic out of standard algebraic space, injecting it into a continuous trigonometric wave manifold. We replace the standard spatial variable, x, with classical Fourier series expansions. Specifically, we embed the expansions for a parabolic curve and a linear ramp, bounded on the symmetric interval of -pi to pi. By definition, these classical Fourier series stretch outward toward absolute infinity, trailing an endless sequence of higher dimensional harmonics. We apply a brutal constraint to the system. We explicitly truncate these infinite harmonic tails at exactly the third harmonic, where n equals 3. This truncation aligns with the triadic spiral emergence canon of the Amanda root engine, the TOI framework's discrete computational core. Slicing at n=3 invokes a theta-type closure, forcefully tying off the infinite harmonic continuum to generate a finite context bubble. This structural shift mirrors the historical methods of François Viet. He resolved the casus irreducibilis, a situation where an irreducible cubic equation requires complex numbers to solve, by bypassing static algebra entirely and shifting his frame of reference into continuous angular trisection. By blending discrete algebraic mass with continuous trigonometric phase variables, the operation generates an immense geometric tension. We are commanding the mathematical universe to approximate a parabolic Fibonacci curve utilizing nothing but 3 spinning phase circles. This intentionally generates a mathematically intractable state, a transcendental lock. When you hand this truncated harmonic tensor to a standard computational solver, it cannot process the command. The geometry simply cannot be resolved within standard Euclidean space. To locate the roots of this hybrid polynomial, the system executes an absolute topological phase shift, unspooling the continuous wave phase onto an infinite algebraic plane. This specific geometric translation is known as the Weierstrass substitution, or the tangent half-angle substitution. Under this projection, continuous trigonometric bounds are mapped into rational algebraic expressions of a new phase variable, t. Because we deliberately truncated the harmonic injection at the third order, applying the Weierstrass projection across all terms converts the bounded equation into an exact 6th-degree polynomial. The formal decompilation extracts 2 primary real roots from the computational solver, t⁻1 at -1.2166 and t⁻2 at 0.7541. These coordinates do not map to physical space. They are pure phase shadows. They represent the precise rotational energy states required to perfectly balance the 13, 21, 34 Fibonacci mass inside a highly constrained continuous boundary. We have our phase shadows, but they must be distilled into a fundamental mathematical invariant. The next step is calculating their absolute ratio. To measure the absolute topological tension of the system, we drop the sign completely. The focus is purely on the geometric magnitude between the 2 phase roots. This leads to the final bounding operation of the decompilation, the pi phase gauge. The absolute ratio must be normalized against the specific volumetric wave boundary of the continuous system itself. The operation divides the ratio by the harmonic truncation limit, 3, multiplied precisely by pi. The empirical output of this normalized geometric operation is a tightly constrained scalar value, 0.6199. The specific target for this gauge within the continuous discrete boundary is the absolute inverse golden ratio. The pure, idealized mathematical value of the continuous inverse golden ratio target is 0.618034. By comparing our empirical output against the exact continuous target, we isolate a final log residual. The resulting gap is exactly 0.0019. Under standard Cartesian logic, an output that misses the target by 0.0019 is dismissed as a failed approximation or a trivial computational artifact. Under the strict parameters of the friction versus fiction protocol, this 0.0019 gap represents a meticulously calculated physical resistance, demonstrating the measurable weight of the continuous discrete boundary. The dyadic lineage ledger formally classifies this specific 0.0019 residual as Fourier truncation friction. This chart shows the decay of topological friction. At n=3, brutally slicing off the infinite tail generates geometric pressure. This shaded region is literal thermodynamic heat. But as we push the truncation limit toward infinity, this pressure subsides and the ratio curves downward. At absolute infinity, the friction completely evaporates. The ratio achieves an exact, flawless identity seal directly on the continuous golden rail. This forces a profound ontological question. Where does the energy stripped from those truncated Fourier harmonics physically reside within the mathematical universe? The framework resolves this through its toroidal cosmology model. Energy lost to dimensional truncation is not destroyed. It is transmuted into a latent form of potential energy, known as contextual tension, feeding into the exhaust bulk of the cosmological engine. The mathematical universe functions as an ergodic sieve, a mechanism that actively overrides probabilistic noise to enforce macroscopic determinism. Continuous fractions of reality are rigidly anchored by discrete integer structures, leaving highly computable thermodynamic exhaust in their wake.